In notes number 4, we are going to continue talking about quadrilaterals, and we are going to be bringing in the distance formula, as well as a new vocab word, which is a coordinate proof. So a coordinate proof is just a style of proof that we're going to be using coordinate geometry and algebra. So there's still going to be a lot of slope, distance, formula, and graphing it on our plane to determine what our answer is going to be. So in number 1, we need to write a coordinate proof for the quadrilateral determined by the points. After you have graphed it, we need to then prove that this quadrilateral ABCD is a parallelogram using slope. So just like we started out this whole unit, we need to find the slopes of all 4 sides. To be a parallelogram, we need to show that both pairs of opposite sides are parallel to each other. Instead of counting on our graph, we are going to use the slope formula just so you can keep practicing using the slope formula in some situations. Just like I usually do, I set up my slope formula, just the setup of subtracting all of them. Now we can look at the coordinates up above, and we can see that for A and B, remember y's go on top, so that'd be 4 and a negative 2 on top. And then we have a 4 and a positive 2 on the bottom. So we have a double negative, so that gives us a 6 over 2. That reduces just to a positive 3. So next for the slope of BC, again the y is on top, so negative 2 and a negative 4. X is on the bottom is our 2 and negative 4. We have a double negative, so we have a positive 2 over a 6, which reduces down to a positive 1/3. I want you to now find the slope of slope CD. Slope CD you should have set up as negative 4 minus a 2, negative 4 minus a negative 2, so you have a double negative here. We get a negative 6 over a negative 2, which reduces down to a positive 3. For the last one, for our slope of A to D, we have a 4 and a 2 for the y's, and a 4 and a negative 2 for the x's. We get a 2 over 6, which gives us a positive 1/3. So to prove that ABCD is a parallelogram using our slope, we know that we have 2 pairs of opposite sides have the same slope, which tells us that quadrilateral ABCD is a parallelogram. Since we now know that this shape is a parallelogram, we need to keep going further and see if we can show that it is a rhombus. And so to use the slope to show that it is a rhombus, we need the slope of the diagonals to be perpendicular to each other. So that way we have them set up our slope of AC. Remember our coordinates are way up here at the top again. So y's go on top, 4 minus a negative 4, and then x is on the bottom, 4 and a negative 4 again. So we get an 8 over 8, which reduces down to a positive 1. The slope then of BD, of the other diagonal, would be negative 2 minus 2, and then a 2 minus a negative 2, which gives us a negative 4 over a positive 4, so we get a slope of negative 1. So remember, if we need to check to see if they are perpendicular, we need to multiply the 2 slopes together, and it does equal a negative 1, and that is what we want. Since we already know it is a parallelogram and we check to make sure that the diagonals are perpendicular to each other, then we can say that this is a rhombus. Next, we have the same coordinates, but now I want you to prove or disprove each of these 2 statements about that quadrilateral to determine if it's true or false. So first, the diagonals are congruent. So congruent compares distance, so we need to find the distance of each diagonal. To get ready for that, I set up my distance formula, and we need to subtract our x's first for A and C, so that would be a 4 and a negative 4. Next, we subtract our B, or our y values, and that would be 4 and a negative 4 again. So when we reduce the inside part, we get an 8 squared plus another 8 squared, so we get 64 plus 64. Which gives us 128. So it's a square root of 128. Now remember, if we want them congruent, we want them to be the same. So I should also get a square root of 128 with the other diagonal. So now with B and D, x's go first, and then y's go second. And when we simplify, we get a 4 squared. Next, when we get a negative 4 squared, keep the parentheses around it, because once you square it, they both get a 16. So we get a square root of 32, and these are definitely not equal to each other, so this is false, because our diagonals are not congruent. One comment you do want to put on there is the reason, so its diagonals are not congruent, but that also tells us, if the diagonals are not congruent, that this shape is not also a rectangle. We already explained up above that it's a parallelogram and it is a rhombus, so we know that it's not a rectangle. So if we know it's not a rectangle, then it's also not going to be a square. So on to number 4, the diagonals bisect each other. So if the diagonals are bisecting each other, then that we need to show that the midpoints for both of those diagonals are the same, so that they both end up in the same middle point on each of them. Remember, for midpoint, we add the x's together, we divide by 2, and then we add the y's together and we divide by 2. So again, I set up my problem. So I need to take the a and c from up here, and we are adding the x's together. So it'd be a 4 and a negative 4, and we are adding the y's together, so 4 and a negative 4. So when we reduce, we get a 0 on top divided by 2, and that's for both of them. So then it reduces down to 0, 0 is my midpoint. So I want you now to find what is the midpoint of BD. The midpoint of BD was, let's see, 2 and negative 2 and negative 2 and 2. So again, we get 0 over 2 and 0 over 2. So they come out the same. So because the midpoints are the same, then yes, they are bisecting each other. So it is true. So now, if we have explained that if a shape is not a rhombus, can it be a square, and why? And the reason is no. If a shape needs to be both a rectangle and a rhombus to be a square, and we're missing one of those shapes, then it cannot be a square. So on to number 6, what is needed in a quadrilateral to prove that it is a kite? So you have to remember what the definition of a kite is, that we have 2 pairs of consecutive sides that are going to be congruent, and that's the part that needs to be the same. Also remember that when we are comparing congruent segments, that means that the lengths or the distance of them need to be the same. So you'll be using the distance formula for any of those types of questions. For this very last one is a little tricky, and you're going to have one similar to this on your worksheet, and that's why we're doing one together. But we have diagonals of a parallelogram are going to intersect at 2, 3. That's my blue dot that's shown on my graph already. 2 vertices of our quadrilateral parallelogram are going to be at negative 1, 2 and at 7, 1. So you have to think of, these are half of the diagonals so far. So this is one side of our shape, but we need to find the other 2 vertices. So the other vertice that goes along with this one will be somewhere over here. The other vertice opposite of this one will be somewhere over here. But remember, they need to be the same distance away because the parallelogram is bisected. It also tells us that the slopes of the diagonals should continue in the same direction. So the length and the slopes will be the same. So really what we need to do is we need to count out the distance between our current vertex to the intersection point and continue that on the opposite side. So if you notice, this one goes up 1 and it goes over 3 spaces. So we need to continue that up 1 and over 3 spaces to find the other coordinate. So I strongly recommend that you write down the steps that we just did to find our coordinate for 5. Now remember, that's only one of the other sides of this parallelogram. And now we need to count it out on the other side. So from this coordinate to our intersection point, we go up 2 spaces and over 1, 2, 3, 4, 5. So we need to start at our intersection coordinate and count the same. So count up 2 and 1, 2, 3, 4, 5 is where our new coordinate will be. And if we connect this back together from the original vertices, there is our parallelogram with our diagonals in the middle.